So theoretically, the maximum likelihood method looks a little bit sophisticated, and let's now see how it works in practice. So let us say that our sample x1, xn follows the binomial distribution with parameters 1 and theta. What does it mean in practice? So binomial distribution with parameters n and p, as you know, is the number of successes in a series of Bernoulli trials, where n is the number of trials and p is the probability of success. And here we see 1 for n. This means that we deal with a trial, with a single trial, with a series of just one trial. So the random variable of this kind that follows this distribution can take only two values, 0 and 1. So if we have just one trial, the number of successes can be either 0 or 1. So, and the probability of success here is the unknown parameter. So we want to estimate this theta. So physical meaning of what theta is just that theta is a probability of success. And so when we say that we have a sample of the size n, this means that we repeat this trial n times, and so each time we get either 0 or 1. So these n random variables, our sample is just a set of zeros and ones. So zeros correspond to failures and ones correspond to successes. So our task is to find maximum likelihood estimator of theta. So in other words, they ask us to find an estimator for an unknown probability, of a random event. As you already know, the natural way to estimate unknown probability is a sample proportion. So the result will be just, you should divide number of successes by the number of trials. So you should divide number of ones in this sequence by n, by the sample size. And so to find number of successes, number of ones, we should add this axis. So the answer is to be sum of x's, that is number of successes, number of occurrences of our event in this series of experiments, divided by n, by the number of experiments. And so now let's apply the maximum likelihood method. The first step is to evaluate this small p function. So as we deal with the discrete distribution, small p is a PMF P of x theta. So this is probability. So according to the definition, this is probability that xi, element of the sample, takes value small x. So as all xi's follow this distribution, binomial with parameters 1 and theta, we can apply the Bernoulli formula for this probability, as we know that for binomial distribution, probabilities of this kind can be found with the Bernoulli formula. But in our particular case, n is equal to 1. So you know that in Bernoulli formula, we have n choose k. So the Bernoulli formula starts with n choose k. And in our case, this is either 1 choose 0 or 1 choose 1. That is why it is always 1. So I'll apply this general formula formally. So formally I have here n, that is 1. Choose x. So we use in general formula, there is n choose k, so here 1 choose x. And then p, that is equal to theta here, theta to the power of x times 1 minus theta to the power of 1 minus x. So one more time, here we have 1 for n, x for k, and theta for p. And this is the Bernoulli formula. As x, this x can be either 1 or 0, this expression, this number of combinations, is always equal to 1. So 1 choose 1 is 1, and 1 choose 0 is also 1. So you can easily prove this using the factorials. So actually, what is left is this expression, x to the power of x times 1 minus theta to the power of x times 1 minus theta to the power of 1 minus x. So what is next? Next step is to evaluate the likelihood function. So likelihood function of x1, xn, and theta is, according to the general formula, product for I from I to n, from 1 to n, of small p of xi theta. So what I am to do is to substitute capital Xi for small x here to this formula. So it will be product for I from 1 to n, not small p, and now I have theta to the power xi times 1 minus theta to the power of, 1 minus xi. So this is how the likelihood function looks in our problem. So now the next step is to find maximum point of the likelihood function. So to do so, we are to differentiate it, to find derivative, to differentiate it over theta, and to equate this derivative to 0 and to find the critical points. But you see that we have a product here, and derivative of a product is a very complicated formula, as we have product of n elements. So the usual way we used to avoid this situation, so we used to avoid the differentiating of a product, is to take logarithm of this function first. So the next step is usually to find log likelihood function. So log likelihood function is natural logarithm of L, of the likelihood function. And so if we do so, we will see that first, logarithm transforms product to a sum. So we will have sum for I from 1 to n instead of the product. And then, so here we also have a product. So this times this. So that is why we will have logarithm, sum of two logarithms. So logarithm of this part plus logarithm of this part. So now we can simplify this expression. As we know from algebra that logarithm of a to the power of b is equal to b times logarithm a. So if we use this formula, we can say that here we have sum of xi times logarithm theta plus 1 minus xi times logarithm of 1 minus theta. So now we are to differentiate this function over theta. As theta is scalar, so we will have only just one derivative. Sometimes it is possible to solve problems of this kind with several parameters to be estimated. In this case, you find several partial derivatives, so you differentiate this expression over each of the parameters, and then equate all them to 0 and solve a system of equations. But in our case, we will have only just one single equation. So, and the first step is just to find the derivative. So, d logarithm L over d theta is this sum, as we know that derivative of a sum is equal to the sum of derivatives. And then xi is just a coefficient, as it doesn't depend on theta. Then derivative of a logarithm is 1 over theta plus 1 minus x is also a coefficient. Then derivative of this logarithm is 1 over 1 minus theta, and times derivative of this expression of 1 minus theta, that is minus 1. So minus 1 divided by 1 minus theta. Now, so we are to equate this derivative to 0. And so the next step is to solve this equation for theta, to express theta via x's. And when we do so, this will be the answer, the estimator. So the first sub-step is to simplify this expression a little bit. And so I'm to find common denominator for these two fractions. And let me do this. So I say that this is the sum. And here I have xi times 1 minus theta minus, as I have minus here, minus xi, minus 1 minus xi times theta divided by theta times 1 minus theta. So this is equal to 0. So now I can multiply both parts of this equation by theta times 1 minus theta. So I want to annihilate this denominator of this fraction, and I can just multiply by this expression, by theta times 1 minus theta. Why I can do so? Because I assume that this expression is not 0. So it can be 0 either if theta is 0 or if theta is 1. So only in case of theta equal to 0 or equal to 1, this expression can be equal to 0. And so theta is a probability, an unknown probability. So let us assume that this probability is not 0 and not 1. So as if it is 0, then we will have only zeros here. If it is 1, we will have only ones here, so only failures or only successes respectively. And in this case, we have just no need to do all this. to estimate theta somehow. So let us assume that theta is not 0 and not 1, and for this reason we can multiply this expression by theta times 1 minus theta. So after this multiplication, only the numerator of this fraction is left, and I also will open the brackets here in the numerator. So after I open the brackets, I'll get xi minus xi theta minus theta then here I have minus times minus plus xi theta. Xi theta. So, and these two are cancelled. And so what is left? Xi minus theta is left. And as you see, theta does not depend on I. So as theta does not depend on I, then we can split it from this sum and just multiply by n. So theta, as theta is inside this sum, it is just added to each other to itself n times, as we have n elements in this sum. So we can separate theta, and instead of putting it inside the sum, just put it outside of it and multiply by n. So we can say that this is sum of x's minus n times theta. And so now we can easily express theta from this equation. So we can easily solve it for theta. If we do so, we'll get that theta is equal to sum of x's divided by n. So, and this is the estimator. The estimator we were asked to find. So, the result of when we solve this equation, the answer is the estimator. So I can now say that this is theta hat, or even more, that this is maximum likelihood estimator. So you see, we got the thing I have told you. So sum of x's divided by n. Sum of x's means number of successes, number of occurrences of our event of interest. So when our event occurs, xi is equal to 1. When it does not occur, xi is equal to 0. So when we add all x's, we get number of occurrences of our event. And n is number of repetitions of a trial of the experiment. So we divide number of occurrences of our event of interest by the number of repetitions of the experiment it is based on. And so we get what we call sample proportion, or a frequency of an event. So that is how formulas for estimators can be evaluated via maximum likelihood method. So other formulas I gave you, so formulas for estimators like sample mean, sample variance, sample quantiles, and so on. So all of them can be evaluated, can be derived with this method. So in case when distribution is given, so here you see we know the distribution of our sample elements. It is binomial with unknown parameter, but the type of distribution is given. So this is a binomial distribution. So this is actually the main condition that makes applying of this method possible. So to use the maximum likelihood method, we must know the distribution type of the sample elements. So if it is given, if it is known somehow, so this method can be used. If the distribution is unknown, totally unknown, so in this case, this method won't work, as we need distribution to find the likelihood function.